Okay, good morning class. So today will be new topics, right? Two-port networks. Basically, you have seen several two-port networks previously in the tutorial problems. It's just that this is not modeled as a two-port network. Two-port network is basically a way of modeling the circuits using 4 variables, and you can see in these circuits that basically you have an port 1 on the left hand side with a voltage 1 and current 1, and on the other side you have port 2 with a voltage V2 and current I2. An important point to take note is that by convention the current is flowing into the two-port networks, right? Basically is from positive terminals, flowing out from the positive terminals. And because there are 4 variables, there will be various ways of modeling these two-port networks. In this course, basically you are introduced with 4 models, right, which we'll go through later on. So as I mentioned just now, you have seen two-port networks many times. For example, the transformers, right? Magnetic couplet circuits, op-amps is also two-port networks. It's just that we did not explicitly put them into 4 variables. In op-amp, for example, we're just interested in voltage in, voltage out. Right here, we include small variables, current at the input port, current at the output port as well. Okay, you have also seen several resistant networks, okay, which can also be modeled as two-port networks. In your senior years, you'll see transistor, right, or other courses. Now, basically, two-port networks is good in modeling a circuit, which is a black box. Okay, this will be what all of you will be doing in L2001B, right, the lab. In the lab, you'll be given circuits, and we don't even need to know the design of the circuits. We're still able to model it as a two-port network. Okay, but of course, in the tutorial, right, circuit analysis, we will use circuit theorems to model the circuits. But take note that in practice, you can actually model a two-port network without even knowing what is the design of the circuits. Right? This means that we don't even need to know what is inside these circuits. We also can model it in terms of these 4 variables. Now, since it has 4 variables, right, V1, V2, I1, I2, it can be expressed in various forms to obtain different types of models. And as I mentioned in this course, you will be exposed to 4 models. The first one is called impedance form. And you can see from this model that on the left-hand side, you have a vector V, right? And you have a matrix Z multiplied by a vector I. Okay, if you look at this relationship, is something like Ohm's law. V is equal to IR, right? V is equal to IR. And this Z basically is called the impedance, right? Remember, in the last 2 tutorials, I have used this slide many times. V is equal to I times Z. Z is called the impedance. Right? Impedance form is good in series combination where you can add up the impedance. For example, Z1 plus Z2, R1 plus R2. So this impedance form is good for series combinations. If you have 2 two-port networks in series, it's good to put them into this form so as to add them up, right, to represent a more complex circuits. You also do that in your lab. Now, basically, impedance forms, the other combinations, right, that we should immediately think of is the admittance form, right? For impedance form, basically, you're given I, multiply by Z, you get V. So same thing over here. If you are given I1, I2, and you have modeled this, right, Z matrix, then given any I1, I2, you can actually use it to calculate V1, V2. So that's the purpose of this model. But sometimes we may also want to do the reverse, okay, meaning that given V, right, given V, we want to calculate I. So in this case, given B, I want to calculate I, then you use the admittance form, because in admittance, you can see over here that I, all right, if you invert this relationship, I is basically equal to V divided by Z, right? Divided by Z. If you call 1 over Z, 1 over ZY, then basically I is equal to Y times V. So given V multiplied by Y, which is 1 over Z, then you can get I. Okay, therefore, similarly, we have this admittance form in the two-port network, and this is good for parallel combinations. If you have parallel combination, you add out the admittance, and then you invert it back to get the impedance, right? For example, if you have two resistors in parallels, you use 1 over R1 plus 1 over R2, you get the overall conductance, you invert it, you get the equivalent resistance. Okay, therefore, over here, we also have this model such that given V1, V2, and if we know the model, we can calculate I1, I2. Okay, this form, as I said, is good for two-port networks which are connected in parallel. Now, you have to remember these models, right? You have to remember these models. And the way to remember is that impedance, right? You write down something like V equal to I or Z times I, right? V equal to Z times I. That means that given I, multiply, get V. But for two-port networks, you know there are 4 variables. So put V1, V2. AI, you put I1, I2. They are vectors. Now, you know that vectors, in order to be dimensionally compatible, you need a 2 times 2 matrix, right? This is your E2001. This is 2 times 1. This is 2 times 1. So therefore, this must be 2 times 2, right? And you can fill out the parameters Z. 2 times 2 must be 4 of them. Okay, after that, just put 1, 1, first row, first column, 1, 2, first row, second column, 2, 1, second row, first column, 2, 2, second row, second column, right? This is what you get. So similarly, for admittance form, write down I1, I2 is your output, V1, V2 is your input. Fill out with a 2 times 2 matrix, put 1, 1, 2, 2, 1, 2, 2, right? So these two you must remember by heart. After you can remember this, then hybrid form, if you look at it carefully, is that you take the first part of your impedance and then put on the upper half, right, of your hybrid form. And then take the second half of your admittance form and then put as the lower half, right, of your hybrid model. Okay, in the sense that you combine these two together. Okay, you merge them, and then you get this form. So that's why it's called hybrid form. It's kind of combining, right? Combining these two together. So in the sense that you have different input, different output. Here you're interested in calculating V1, I2 using I1, V2. So once you can remember these two, right, hybrid forms, right, can come out quite naturally. And lastly, you have this also very important model. It's called transmission form. Now, as I mentioned to you, I1, I2 are by default inflow, right? Inflow. But transmission means that you want to transmit, for example, from port 1 to port 2 in this direction, right? Transmit from here, left-hand side to right-hand side. Transmission line, for example. You have a power generator, you want to transmit it to a factory, right? So it has to be flow in the other way around. Okay, but because two-port network is defined by default, inflow is positive. In this case, we need to invert it, right? If inflow is positive, then outflow will be negative. Therefore, we put negative I2 in the transmission model just to indicate that we want to flow, right, from left-hand side to right-hand side, port 1 to port 2. And of course, here, the parameters will be then, right, V1 I1, V2 I2. Right? Given V2 negative I2, find V1 I1. And of course, you can invert it the other way around by finding the inverse matrix here as well, in all cases. And over here, right, these are just definitions of your matrix. Right? Actually, you can also call it T11, T12, T21, T22. Right? But in the beginning, people call it A, B, C, D parameters. Right? So this is A, B, and C, and D. So therefore, this too, as I said, has a physical meaning. Right? Impedance V is equal to ZI, admittance I is equal to Y, V, hybrid, combine these two together. Transmission, right, is to transmit from the left-hand side to right-hand side. So we have all these four models. You need to remember all these four models by heart. Right? You must remember it by heart. Otherwise, you won't be able to model it. Okay, once you can remember this model by heart, okay, the rest basically is to use the methods in week 1 and week 2 again to manipulate, right, to write down the equations and then rewrite the equation into this form, right, which I'll show you later on. Okay, but before that, let us go through some of the basic concepts that you will learn, that you will do in the experiment. Right? Remember, I said that two-port networks has 4 variables, and the good thing about two-port network is that you can model the circuits even without knowing what's inside. Okay, this means that there must be a way, right, to determine all the 4 parameters. Right, these are the 4 parameters in each circuit, depending on which form that you want, by using certain experimental procedure. Right, so the key advantage, right, remember, of two-port network is that you can model it even without knowing what's inside. So this is good in the sense that if you have some commercial circuits, right, which are protected, okay, so basically we can do some experiment to try to model it as the two-port networks, depending on what variables we are interested to find out, and then from there we can analyze it, right, based on the two-port network model. Now, firstly, right, we have, let us look at how do we identify the parameters Z11, Z12, Z21, Z22 of an impedance model. Okay, the key idea is that you set one of the input to 0, right, at a time. Suppose that you set I2 to 0. Okay, if I2 is equal to 0, then there's no more I2 in your model. Then there's only I1. This means that instead of 2 inputs, you restrict it to 1 input only. Then you have a more simpler model, which only have Z11, Z21, right? So if V1, V2 are known, if I1 is also known, then obviously you can calculate Z11 and Z21. Okay, this means that you should set these experimental conditions that to impose I2 equal to 0, right? So as to calculate Z11 and Z21, right? By knowing what is V1 I1 and V2 I1. So the next question is that how do we set I2 equal to 0? I2 is here. When you want to set I2 equal to 0, it means what? You open, right? You open. So this is what you should do. Go to the two-port networks, leave port 2 as open. If there's something connected there, then remove it. If there's a load connected there, remove it, then it will be open. Okay, when it is open, remember that we have current as input now, only one input. So, and this input is at port 1, I1. So go to port 1, put in an independent source, right? You have done the experiment. You know that you can basically connect a power supply, current, voltage to a circuit. So this is a current source. Put a current source over here, for example, 1 ampere, right? Something similar to your Thevenin's theorems. You inject something inside. Okay, then you measure. What do you need to measure? When you inject I1, you need to measure V1, V2. So the next step is that you measure V1 and V2. Okay, since I1 is known, by measuring V1 and V2, we can actually calculate Z11 and Z21. So the whole procedure is shown in this slide over here. Okay, because we want only one variable, I1, we open port 2 so that no current can flow in port 2. Then we inject a known current into port 1, and then we do measurements. For example, connect some voltmeters to measure V1 and V2. Knowing V1 and V2, and I1 is known because you inject it, for example, 1 ampere, right, 2 amperes or any values, because your V1 and V2 will be proportional, right? This is linear circuits. And then we can calculate Z11, Z21. Now this is basically experimental procedure, right? Experimental procedure, though you can use this to analyze your circuits, but if the circuits model is known, right, it's easier to analyze it in another way, which I will go through in the tutorial problems later on. Okay, but you need to understand this experimental procedures so that, right, when you do the experiment, you can follow this. And it can be used in your theoretical analysis as well, but as I said, right, there's another way which is easier if the model is known. Now you have obtained these two, Z11, Z21, right, by leaving I2 open. So if you go to the other one, that means that you set I1 equal to 0, right? If I1 is equal to 0, then we have only I2, which means that now we are trying to identify the other two parameters, Z12, Z22. Now here, I2 is now your input, and V1, V2 are your outputs. If you know what is I2, and if you can measure V2, then you can calculate Z12, Z22 as well, right? Because the only unknown would be your Z parameters. So same thing, this is what we will do. We will leave port 1 open now, because why? You want to set I1 equal to 0 now, right? So the other way around. Then you inject a current source, say 1 ampere at I2, right? So this is known, I2 is known. Then you use voltmeter to measure V1 and V2. Here is the open circuits voltage. Then basically I can get everything which is required to calculate Z12, Z22. Okay, therefore, you can get all the 4 parameters by doing 2 experiments. One is to open port 1, the other one is to open port 2, so that you can focus on 2 parameters at a time to identify the 4 parameters. So this is for impedance form. If you understand the concept, then you can easily do it for other form. So the key idea is to turn, right, one of the input to 0 first, because you have 2 input, 2 output. Put one of the input to 0, focus on 2 parameters, identify them, right, by injecting a known input, okay, and then measure the output, then calculate the parameters. For example, in admittance form, your input will be your V1, V2, your output will be your I1, I2. In this case, I need to set one of the input to 0. For example, V2 equals to 0. If V2 is equal to 0, then you have only one input, V1. You have 2 output, I1, I2. Okay, if you know what is V1, if you measure I2, you can use them to calculate Y11, Y21. Okay, which means that you need to impose the condition that V2 is equal to 0. How do you make V2 equal to 0 short? Short where? Port 2, right? Short port 2. Port 2, short circuits means that you have no resistance. V is equal to IR, R equal to 0, means that voltage is equal to 0. Okay, with V2 equal to 0, then inject a known voltage now, because your input is a voltage. Say 1 volt, right? 1 volt. Measure I1, I2 using ammeter. Measure using ammeter. Then use that to calculate Y11, Y21. So similarly, right, if you want to determine the other two parameters, then in this case short V1. Short V1, so that you have the other two parameters, Y12, Y22. Then put in a known voltage, say 1 volts, measure I1, I2, and then calculate Y12, Y22, right, based on I divided by V. Right, here you can also see that I over V, right, I over V is admittance, V over I is impedance. Any questions? Okay, so this is what we can do in the experiment. Just make one of the input to 0, measure, right? Measure the other output by sending in a known input. Now, in this tutorial, right, we need to determine whether a network is reciprocal or not. So reciprocal network is basically a special class, a subclass of two-port networks. Two-port networks is very general, right? But there are some specific networks with some properties. Right? In this case, here we are interested in this particular structures called reciprocal or special property, okay, called reciprocal networks. Right, let me explain what do we mean by reciprocal. Firstly, right, take note of this comment over here. If we connect the same input voltage source to one of the port, right, that means that if you put it at port 1, okay, for one experiment, and you do it at port 2 for the other experiment, notice that they must be the same voltage source. Right? For example, if you put 1 volt, then the other side should be 1 volt. Okay, after that, measure the short circuit current of the other port. So over here, you put the voltage source as port 1, then you measure the short circuit current at port 2. Right? That means you short it, connect an ammeter there. So same thing, if you put your input at port 2, right, the other way around, okay, and then similarly you measure the current at port 1. Now suppose that if you put in the same input, it produces the same current, then this network is called reciprocal, right? So basically, if you put the ammeter there with the same voltage on either side, whether you put port 1, port 2 as your input, on the other side you get the same current, right? This means that it's reciprocal. Now, if you look at this circuit carefully, if port 2, right, V2, port 2 is short circuit, it means what? V2 is equal to 0, right? V2 is equal to 0. Remember just now one of our experiment, we set V2 equal to 0, right? Set V2 equal to 0, all right? You can determine this Y21, I2 divided by V1. So this is exactly the same, I2 divided by V1. Right, it's actually your Y parameters. I2 divided by V1 is actually Y21. So over here, this experiment, right, in this case, you set V1 equal to 0. Okay, if you set V1 equal to 0, and then you calculate this Vs and your currents, I2, I1, V2, then it's actually this, right, Y21. Right? Let me check I1 V2, right? I1 V2. So I1 V2 is actually Y12. So one is Y21, one is Y12. Okay, this basically means that if Y21 and Y12 are the same, it means that this network is reciprocal, right? Because why? Your I2, right, will be equal to same magnitude. Let's call it negative I, right? I just reverse these directions because by default, right, your I1 is flow this way, right? But if you measure it using ammeters, right, basically you get a negative value. You should indicate it as a negative value because your measurement is this way. If by default it flow this way, then you should put a negative value. So if you put same inputs, Vs to V1, V2, and then you get the same current, then this means that y21 is equal to y12. Okay, therefore, to check whether a network is reciprocal or not, right, one way is that you do experiment, put in Vs at both sides, measure I at the other side, right? This is what we do in the experiment. In theory, right, we just check the model, if we have the model, whether y21 and y12, right? y21 and y12, that means after you have calculated the models, by circuit analysis, you check whether y21 is equal to y12. So if you look at your notes, right, you have these conditions, y12 equal to y21, right? It actually means this. You put in voltage at either side, you produce the current, same current at the other side, right? This is what it means. And this means that it corresponds to these parameters. Now, the other three conditions actually is derived based on this condition, right? Based on these conditions, let us ignore it first. Okay, and if you have a circuit in other form, right? Remember, actually we can transform it to Y form, correct? We can transform it to Y forms. Then actually we can then compare, right, the Y parameters based on the other parameters. Okay, at this stage, just ignore it first. I'll go through that later on. Okay, the next thing I want to discuss is that the model can be converted from one form to another. Okay, for example, suppose that you have an impedance model, you have model impedance models. Okay, you want to convert it to admittance model, then actually you can just use matrix theorems, right? Calculate the inverse of this matrix. 2 times 2 is quite easy to calculate. Then you can get the admittance form. Okay, and for other models, right, it's also quite easy to convert through algebraic manipulation. Right, of course, as I said, you need to remember the particular models. Right? If you want a hybrid model, you must be able to write down either this or this, right? Otherwise, you won't be able to proceed. Now, let us look at how we can convert impedance form to hybrid form. First thing that you need to do is to compare the models and look for one models, right, if possible, with all the same parameters. For example, by comparing the last two, right, actually you will see that they all consist of V2. You have V2, all right, and then you have I1. You also have I2. This basically means that it's just a matter of rearranging this equation into this equation. For example, here V2 is your output of interest. Here I want I2 to be my output of interest, which is this one. Okay, therefore what I need to do is just to rearrange these equations. Okay, by putting I2 as my subject. Okay, the rest I just put it to the other side of the equation. Then I can get I2 in terms of I1 and V2, which is what we want over here. So basically H21 is this, right? And then H22 is this, okay, which means that I can convert it from one form to another through algebraic manipulation. Now I cannot start with equation 1, right? Because there's no way that you can manipulate it into this form. They have different variables, this V1, I1, I2, this V1, I1, V2, right? So you can't do that. But however, after getting this one, after getting these equations, right, you can check this equation. I want V1 to be expressed in terms of I1 and V2. This is what I want, all right? I want V1 to be expressed in terms of I1 and V2. So I1 is okay. I keep I1. I do not want I2. Right, because I want only I1 and V2. But I1 is already obtained here in terms of I1 and V2, which means that I can then substitute this into here. By substituting this whole thing into here to replace I2, then everything will be in terms of what I want, which is I1 and V2, right? So I only want I1 and V2. After that, just group I1 together, you get your H11 parameters. Then your H12 parameters is basically this. Okay, that means that you can actually transform it from one form to another, right, through either matrix theorems or simply just algebraic manipulation. Okay, I'll show you one more. Suppose that I want to transform impedance form to transmission form. Right? As I said, firstly, you have to be able to write down this. I want to express V1 I1 in terms of V2 and negative I2, right? V2 and negative I2. So this is my objective. Okay, then I compare the circuits. All right, same thing. This is good to start with because they have exactly the same three sets of parameters. I1, I2, I1, I2, and V2. So from equation 2, I want to turn I1 into my output. Through algebraic manipulations, I get I1 in terms of V2 and negative I2, which is this equation. This means that your C parameters is 1 over Z21. All right, your D parameters is Z22 divided by Z21. And once you get this one, it's easy to get the other one because you can just substitute this into here, replace your I1, and we can get everything in terms of what we want, which is V2 and I2 only, right? We want V2 and negative I2. Okay. Any questions? So from here, you can see that, right, the key ideas is just to write down the equations in any form and then try to rearrange it into the desired model which you want, right? So when you write down the equation, you just put it in any form, so long as it consists of only the 4 parameters, I1, I2, V1, V2, and then you rearrange it into this form. Okay? Now let's go back to the slides, right? Let's go to the slides where I extracted out from your lecture notes. So this table you need not remember. This table is basically what I mentioned to you just now. Okay, you can transform the model from one form to another, right? But you do not remember these tables. This table is going through what I did just now and put it into this form, but you can see it requires lots of memory, right? And it's not necessary because you can derive it in 1 or 2 steps. Given one model, you just do some algebraic manipulations or find the inverse matrix. You can actually transform it from one form to another. Right here, I just let you know how to use this table. Okay, here is that given a z parameters, right? If you want to convert into y form, you use this, right? If you want to convert into hybrid form, you use this one. If you want to convert it into ABCD form, you use this. That's why you can see that given all the z, you can find the y, h, and ABCD. Right? Similarly, over here, given y, you can transform it into z form, h form, and ABCD form. Right? And similarly, you can deduce the rest. So these columns, or this row, basically represent all your models in Y form, right? This represent all your model in Z form. This represent all your model in H form. Okay, but they are transformed from other form. So this columns over here, right? Basically, you have a Z transformed to Y form, right? And over here, you have H form transformed to Y forms. And over here, you have ABCD form transformed into Y form. Right, so remember these conditions that if a network is reciprocal, Y12 is equal to Y21, correct? Y12 is equal to Y21. So if you have other form, then you transform into Y form. If you have Z form, transform into Y form. H transform into Y, right? ABCD transform into Y. Okay, then actually we can also retrieve the conditions for other parameters, right? In particular, Y12 must be equal to Y21 for a reciprocal network. This means that for Z form, after you transform into Y form, right, you just compare these two conditions. This must be equal to this. Okay, they have the same denominator and they have the same sign. So therefore you get this condition, Z12 is equal to Z21. So Z parameters is easy to remember, right? They are the same. Right? Just compare the elements 1, 2 with the elements 2, 1. If they are the same, then it's called reciprocal. Okay, well, for hybrid form, after you transform into Y form, this is your Y12, this is your Y21, then that must be equal, right? If you compare them, same denominator, cancel out, but careful, there's an opposite sign. So this one I won't say it's difficult to remember, just remember this two, invert the sign, right? Invert the sign, and then you get this one. Okay, or you cannot remember, then you can actually base on any form, right? If you have a model in this form, okay, which you think easier to remember, you put it into this form first, then transform it into the other form by manipulation. So lastly, for ABCD parameters in Y form, transform into Y forms, you compare these two, they have the same denominator also, right? And then here, this delta T is actually the determinants of your matrix, okay, which means that delta T must be equal to 1, right? Negative, negative, equate them, cancel out. So this is also not difficult to remember. Take the determinants, check whether it's equal to 1, right? Then that will be your conditions for checking a reciprocal networks for ABCD. Any questions? Okay, so we have gone through, right, some of the basic concepts which are required for tutorial 8. In particular, you can see that we need to model these circuits in Z parameters form and check whether is it reciprocal or not, right? Which means that you need to check whether Z12 is equal to Z21. Okay, after you get the Z parameters. Okay, basically here, firstly, you need to remember this, right? Either this form or this form. Otherwise, you can't even start, or you remember wrongly, you get the wrong model eventually, right? So Z parameters, given current, find voltage, right? Given I1, I2, find voltage. So you can actually write down this V1, V2, right? Input I1, I2, two input, two port networks. Then fill up with Z parameters. And to differentiate them, right? First one, first row, first column, first row, second columns, right? Or second equations, first elements, second equations, second elements. Right? In matrix form, is first row, first column, first row, second column, second row, first column, second row, second column. So once you can write this down, right, is already half done, because the rest is just circuit analysis in week 1 and week 2, and then try to rearrange the equation into the desired form that you want. Right? So this is your target models. You write down the equations in terms of the 4 variables, V1, I1, V2, I2, and then try to rearrange the equations into this form. Right? For example, here, if I use mesh analysis, this is my I1. Right? Remember, I2, I1 is all inflow. Right? So you define this way. This is your I2. The mesh analysis says that apply Kirchhoff voltage law around the loop. So here you have V1, right, equal to the voltage across the 4 ohm resistor, 4I1. Now here, the current flowing through the 2 ohm resistor is I1 plus I2, right? Because here you have I1, here you have I2. Okay, as I mentioned, if you're not sure, just use Kirchhoff current law, I1, I2, inflow equal to outflow, I1 plus I2. And this is the voltage across the 2 ohm resistors. And here you have an independent source depending on V1, right? So you have V1 over here. Okay, basically this is what it means. If I start from the ground, 0 volts, I climb out V1, right? So I climb out V1 at, okay, then this is passive, always flow from high to low. I climb up another 2 I1 plus I2. Then here, this is passive, high to low. I climb up another V1, right? Then I reach this voltage, which is V1, because this is 0 volts at another V1. So left hand side equal to right hand side. So similarly over here, right? Right hand side V2 voltage, and here I climb up by V2, for V1, okay, and then I climb up by another voltage across the 2 ohm resistor. You can see this part are the same because this is a common branch, right, between these two. And then I only need to actually add up this voltage across the 3 ohm resistors, high to low, right? High to low, so low, negative to positive, pass. As I said, this is one way of writing down the equations. You can write it using any way that you want. For example, increase, you put positive, right? Or increase, you put negative. They all give you the same equation. Now, basically, everything is the same, except that we leave the equation in terms of the 4 variables, I1, I2, V1, V2, because we want to express, right, 2 of them in terms of the other 2. In this case, we want to express V1, V2 in terms of I1, I2. So remember that. Okay, this is the overview, the steps which we will involve in solving the problems. First, we use circuits theorems to write down the equations, same thing with V1, V2, but in terms of the 4 variables, right? In terms of the 4 variables. Then we write down the desired forms and then see how we can rearrange this equation into the desired form. Okay, for example, I would now start with equation 1 because here I have V1, I1 and I2. Okay, here V1 is my subject. Here V1, right, is also my subject, which means that I only need to move this to the other side of the equations. Then I will get this model. Okay, so this is what I do from equation 1. I just move this to the other side of the equation. I get -3, right? Then divide by -3. I basically get my first model in terms of the Z parameters. So this is my Z11, this is my Z12. Okay, after you get these equations, then look at the other equations. You want V2, so no problem, this is what you want, V2. And you want I1 and I2. Right, so I1 and I2, no problem. But I do not want V1. Right, I do not want V1. Therefore, I substitute V1 in terms of I1 and I2 into it. And after that, everything will be in terms of I1 and I2 only, because V1 can be expressed in terms of I1 and I2. Right? This means that by substituting this into here, right, into here, I can get this, right? This is my V1. And after that, simplifying it carefully by grouping I1 and I2 together, I can get the next equation. So I hope everybody get the ideas. Write down the equations using Circuit's law. Right? Write down the equations using Circuit's law. Mesh analysis, nodal analysis. In terms of the 4 variables, two-port network has 4 variables. Then do algebraic manipulations, rearranging the equations so as to get your input-output right, depending on what you want to model. For example, Z parameters, I1, I2 input, V1, V2 output, right? So you need to rearrange the equation. Now, basically this is sufficient, but if you want to put it into matrix forms, right, also can. Put this into a matrix form, 2007s. Okay, then actually you can then find the inverse matrix to transform it to another form, right? Also easily. It means that you can apply matrix theorems thereafter. So remember, we need to check whether is it reciprocal or not. In fact, here Z12 is not equal to Z21, right? Z12 is not equal to Z21, therefore it's not reciprocal. Any questions? Okay, let's look at question 2 again. Y parameters, just now Z parameters, now Y parameters. Check whether is it reciprocal, right? Right, here, be careful, there's a dependent source. This means current source, right? This means current source. The current is depending on V2. Right? So the whatever value here will be amplified by 2, and this current over here will be 2V2. So we know that this current is 2V2, and we have to recall that Y parameters means this, right? Y parameters means admittance. So sometimes it's called Z parameters or impedance, right? Parameters. Similarly, over here, sometimes it's called Y parameters or admittance parameters, right? You have to remember that. And Y parameters basically is the other way around. Given V1, V2, find I1, Y2. So write this down. Given V1, V2, find I1, I2, which means that you want to express I1 and I2 in terms of V1 and V2, right? So we will write down the equation first in terms of the 4 variables. And then we try to put it into this form. So first step, write down the equations in terms of the 4 variables of the 2-port networks by using circuit analysis. Then we rearrange the equations into this form through algebraic manipulation. All right, first thing, we need to write down the equations in terms of the 4 variables, right? Must be in terms of the 4 variables only, so that you can rearrange into this form. Now, if there are some variables which are not in terms of V1 or in terms of the 4 variables, then try to relate them. For example, right, if you use nodal analysis, then over here this is V1, right? Over here this node is V2. Okay, but here there's a node, right, which we do not know. Then you have to call it Vx, right? Anything you do not know, you call Vx, or you just call it V, right? It's just a notation. Okay, now this node is not known, and the purpose of modeling 2-port network is to express them in terms of the 4 variables, right? Not necessarily all. Just try to relate to some of them. In this case, I'll try to relate to V1 and I1. Right? It's easier to relate to V1 and I1 because why? This node voltage, right? If you look at this, this is V1. Then you have a 1 ohm resistors. At the other side, you have Vx, right? At the other side, we have Vx, and this current is I1. So you can write this now directly. Vx, current flow from high to low, correct? High to low. So V1 minus the voltage across the 1 ohm resistors, which is 1 ohms, multiplied by current flowing through it, I1. Then it's equal to V1 minus I1. Okay, if you're confused with this, never mind, just put this Ohm's law. V1 minus Vx, voltage across the resistors from high to low, divided by 1 ohms, right, is equal to what? Your current I1. Same thing, you get these equations. Vx is equal to, right, Vx is equal to V1 minus I1. Just rearrange this equation. Right? Vx will be equal to V1 minus I1. So what's the purpose of doing that? everything must be expressed in terms of the two-port networks variable. Here I express in terms of V1, I1. All right. How about V2, I2? Actually also possible, right? But this is easier. Okay, which means that if you want to express in terms of this, first I need to know what is this current, correct? I need to know what is this current. Okay, but this current is easier. This current is in terms of I1. So I can get this easily. Now this one you need to do additional steps, right? Possible, but not the best way, because you need to spend more time. To find this current, I need to find this current. This is I2. And this current is what? V2 divided by 4, just Ohm's law. Voltage across it divided by 4. So inflow equal to outflow. I2, right, is equal to this current. Okay, if you call it I, right, if you call it I2 is equal to V2 over 4 plus I, then you can calculate I, right? After you get I in terms of I2 and V2, then you can do similar things, right? This is your V2, this voltage is V2, and this Vx, currents times 2 ohms, right? You can relate them, and you can also express your Vx in terms of V2 and I2. It's also possible, but more step is involved, right? So I would say that this is easier, right? Just focus on this one. Any questions? So now I have expressed my node voltage in terms of my two-port networks variables, right? So that the rest will be easy. When I perform nodal analysis, I can write down equation in terms of my two-port networks variables, the 4 variables. Right, so let's proceed to write down the equations. If I take Kirchhoff voltage law at this node now, then inflow, right here, the inflows, right, normally you write V1 minus Vx divided by 1. Okay, but for two-port networks modeling, right, you shouldn't do that. Let me clear this first. Because the whole idea is that you would like to write down the equation in terms of all these 4 parameters, right? Any of the 4 parameters. Here, this is already I1. So just put down I1 directly, right? Now, even if you try to do this V1 minus Vx, remember Vx is this. So V1 minus Vx, basically you still get I1, right? Divided by 1, you still get back I1. Then you spend additional steps, write down the equations, and go back to the same thing again. So here, as I said, current is known, I1. We need I1, just leave it as I1, right? So this I1 plus, okay, next one will be this current, which is 2V2. Also in terms of V2 is okay. So we leave it, right? No need to do anything. Only the other one, okay, which is this one over here. Okay, here we put inflow as well. Okay, which means that over here you have V2, this node voltage is V2. V2 minus Vx divided by 2 is the current flowing into the nodes through the 2 ohm resistor, but Vx, right, should be expressed in terms of the two-port networks parameters, variables, V1, I1. So we put it into here. Then everything is in terms of V1, V2, I1, I2, right? Look at equation 1. I have no other variables except these 4 variables. Then after that is a matter of rearranging the equations, right, into the desired form. So far what we have done is that we use circuit theorems to write down the equation in terms of the 4 variables, right? The 4 variables. Not necessary all, right? Just write down in terms of the 4 variables or some of the 4 variables. Then you can get the equations. Okay, after that, check whether is it possible to rearrange them into one of this form that you want. Okay, it is possible because why? Here we have I1, V1, V2, right? I1, V1, V2. We don't have I2, so we should choose the first equations. That means that I want I1 to be expressed in terms of V1 and V2. Okay, the rest is just to simplify the equations. So here I multiply by 2, I get the next equation. Then I group I1 together, right? I group I1 together, negative, negative become positive, so I have 3. Then divide by 3, I get I1 in terms of V1 and V2, which is my first equation. So I get this first equation. Okay, after you get the first equations, proceed to the other node, right? We have done case here at this node. Proceed to another node, write down another equations by Kirchhoff current law. So again, this is I2, just write down I2 inflow. Okay, and then here I will assume inflow as well. Vx is V1 minus I1, right? Vx minus V2, this node Vy is actually V2. Vx minus V2 divided by 2 ohms is the current flowing into the node through the 2 ohm resistor. So we have this. Now this one, let's assume outflow because normally you flow to ground. So V2 divided by 4, right? V2 divided by 4 is the current flowing through the 4 ohm resistor to the ground. And therefore we write down another equations in terms of the two-port network's variables, right? So we get these equations. Let us look at the other equations, right? We have done this one, so we need to put it into this form. I2 in terms of V1 and V2. Okay, we have obtained these equations through circuit analysis, Kirchhoff current law, right, at this node. So I want to put it into this form, right, which means that I want my I2 to be my subject, so as to express it in terms of V1 and V2. So firstly, I put I2 as my subject, rearranging these equations. Right here, first I multiply by 2, multiply by 4 first. I get the next equation. Then I put I2 as my subject, express it in terms of the other 3 variables. Right here we have 4 variables. Okay, then look at this equation. You want V1 and V2 only. You do not want I1, right? You do not want I1, but recall I1 just now has been expressed in terms of V1 and V2. Okay, which means that you can just substitute this into here. Then you can get everything in terms of I2 only, right? So here I divide the equation by 4. Then I substitute this into here, so that everything is in terms of only V1 and V2. Then I group the coefficients of V1 together, group the coefficients of V2 together. I get this form, right? I2 is now expressed in terms of V1 and V2 only. Any questions? So I get the 2, right, equation which I want. And this is my Y parameters model. So this slides basically summarize everything. Okay, you apply Kirchhoff current law at node 1, you write down equation 1. Apply Kirchhoff current law at node 2, we write down equation 2. The key idea is that anything, right, which is not in terms of your variables, try to express it in terms, right, of the 4 variables. And the rest, right, just use the variable directly. For example, this I1 just use it directly. This I2 just use it directly, right? And this currents will be V2 divided by 4, for example, expressed in terms of the 4 variables. Then look at what you want. Rearrange the equation into this form, and you'll be able to get the desired form, right, that you want. And in this case, we want to express I1, I2 in terms of V1 and V2. Okay, it's also not reciprocal because this is not equal to this, right? Or this is not equal to this. Right, this means that if you pump in the same voltage on either side, right, it will not produce the same short circuit current on the other side. Any questions? Now you can see that the tutorial basically is going through the 4 models, right? Just now we have Z and Y. Now we have H parameters. Same thing, check whether is it reciprocal or not. Okay, again, you have to be able to remember this, right? H parameter is in this form, given I1, V2, find V1, I2. Okay, as I said, is basically combinations of this, right? By deleting this and combine them, basically you get this one. Okay, or you just simply remember what is the output, what is the input. I want to express V1, I2 in terms of I1, V2, right? In this case, V1, I2 in terms of I1, V2. Okay, the rest is to write down equations using these 4 parameters, 4 variables, and then try to rearrange them into this form, right? So first, let us use mesh analysis. This is my I1. This is my I2, right? Remember, your convention is that it's inflow. Okay, for this one, this loop has a known current, which is called 3I1, right? 3I1 in this direction. Okay, if you start from mesh 1, then you can write down V1 is equal to 4 I1 plus I2, right? Because this current, this is I1 downwards, right? This is also downwards. So I1 plus I2 times 4 give you V1. So this is my first equation from mesh 1. Okay, for mesh 2, just go through this loop also. Right, current through the 2 ohm resistor, be careful. Right, current flowing through 2 ohm resistors will consist of firstly I2, okay, plus 3I1, right? 3I1. So in the same direction, you add them up. I2 plus 3I1 times 2 ohms is the voltage across this, right? Resistor. Okay, this part is the same, common branch, for I1 plus I2. I need not waste time because they are the same. And we can put it over here. This is impedance form, correct? V1 is in terms of I1, I2. V2 is in terms of I1, I2. There's only I1 and I2. Okay, which means that I am now trying to transform impedance form into hybrid form. Okay, and it can be done by algebraic manipulations. And in fact, at this stage, right, we already know that it's not reciprocal. Why? Because Z12 is not equal to Z21. So we can actually conclude already that it's not reciprocal. Okay, let's transform it into hybrid form. Okay, hybrid forms, look at the desired form first, and then compare with the current form, obtained through circuit analysis. Right, I will start with equation 2. Why? Because they have the same sets of parameters. V2, I1, I2, V2, I1, I2, which means that it's just a matter of rearranging the equation, right? by turning I2 into my subject. I express I2 in terms of the other two parameters, the two variables, I1 and V2, right? Just by rearranging the equations, divide by 6, and I can get the first models, or rather the second equations of the model. So next, after you get this model, right, after you get this equation, which is this, you can see that then you go back to the other equation. I want V1 to be expressed. I want V1 to be expressed in terms of I1 and V2. So I1, no problems. I want to keep I1. I do not want I2 because I want V2 and I1 only, right? Therefore, you go to here. I2 is expressed in terms of I1 and V2 already. We replace this by this. Replace this by this totally. Then you get everything in terms of I1 and V2, right? I1 and V2, which is what you want. I1 and V2 only. So the last step is to just to substitute equation 3 into equation 1, replacing I2. Then everything will be in terms of I1 and V2 only. Grouping I1 together, you get your H21 parameters, and putting V2, right, coefficient of V2, you'll get H22. So this is the overview. I write down equations using mesh analysis in terms of the 4 parameters. Right? I don't really need to care whether is it in which form. Just write down all the equations in terms of the 4 parameters. Then compare with the desired form that you want. Right? As I stressed, you must know this desired form, otherwise you can't even put it into this form. Okay, after that is a matter of starting, right? Try to start with the equation if possible, with the same 3 sets of parameters. Then you will be able to directly manipulate it into the form by just rewriting the equation. And the other equations, right? If you can rewrite it directly. If you cannot, then after you obtain these equations, just substitute it into the other one, and you'll be able to get the desired form that you want, right? Either directly or by rearranging the equation again. Any questions? And remember that you can also check whether the network is reciprocal or not through the H parameters, right? But be careful of the sign. Okay, in this case, the values are not the same, right? So whether the sign is the same or not, it doesn't make much difference. But if they are the same values, right, then you need to check the sign for H parameters. Any questions? So I hope everybody get the ideas, right? Write down the desired form that you want. Use circuit analysis to write down equations in terms of the 4 parameters, 4 variables. Okay, then rearranging it into the form that you want. So this is basically what we do for the 2-port networks modeling. Okay, let's look at these circuits again. Now we need ABCD parameters, okay, which is the transmission form. Now transmission form basically means that you have to reverse this current, negative I2, right? Transmissions from generator to factory, for example, right? So this current should be reversed in the directions of the transmission, okay, which means that we will like to have a negative I2 over here, right? So this is important. You determine the sign of your B and D. Okay, let's look at this circuit closely. Okay, by conventions, actually your I2 is inflow into the port, right? Into the circuits from port 2. So we reverse it this is negative I2, and this is already defined for you in your circuits. But if it's not defined this way in your circuits, if I2 is defined this way, what you need to do is to put negative I2 the other way around, right? This is what we are interested in. And for I1, it doesn't matter because it's already in this direction, right? So these are directions of the transmission. Okay, next is to note that anything which is not in terms of the 4 variables, try to express them in terms of the 4 variables. If here we have a dependent source, 3Vx, this is a voltage source, right? The voltage here is depending on Vx. Vx is here. Vx is the voltage across the 50 ohm resistor. Now, as I say, anything which is not in terms of the variables, express them in terms of the variables. Here, Vx is the voltage across the 50 ohm resistors, and this is I1. This is I2, right? This is I2. So this current is I1 plus I2. Kirchhoff current law. Inflow, add up to become your outflow. So I1 plus I2 times 50 is Vx, okay, which means that this is 3 Vx, 150 I1 plus I2. Okay, with that, everything is in terms of the 4 variables, right? Then you can proceed to use circuit analysis to write down the equations in terms of the 4 variables. So this is what we will do. We will now proceed to use mesh analysis to write down 2 equations in terms of the 4 variables, knowing that Vx can be expressed in terms of I1 and I2, right? So firstly, starting from mesh 1, go around the loop. This is V1, right? And here, if you add up Vx, correct? Vx, what is Vx? Vx is 50 plus I1 plus I2. So right now, Vx, 50 plus I1 and I2. Okay, here current flow from high to low, correct, in these directions. So voltage is Ohm's law, 50 times I1, sorry, 10 ohms times I1, right, increase. That means that here you start from 0 volt, climb up Vx, climb up 10 times I1, then you come to this potential, which is V1. Okay, on this side, this is V2, right? This voltage is V2. You climb up from the other side, come to here, is also V2. So I add Vx over here, add Vx. And then here, this is negative to positive to negative, so drop, right? This is negative to positive, increase. This is positive to negative, drop. So I have negative 3Vx. Then I come up to Vx. And negative 3Vx plus Vx is negative 2Vx. Okay, remember Vx is 50 I1 plus I2. Put into here, you get negative 100 I1 plus I2, which is negative 100 I1, negative 100 I2. So I get my equations in impedance form. Okay, if the question say impedance form, then stop here. But now we need to transform it into this form, right? Transform it into this form, and as I said, normally it's just algebraic manipulations. Okay, again, by the way, we already know that this is not reciprocal because these 2 parameters are not the same. Z12 is not equal to Z21. Okay, but we still need to put it into hybrid form, which is called the transmission form. Okay, if you compare the equations, again, equation 2 is good because you have all the 3 parameters that you want, right? So I just need to turn I1, right, in terms of the other 2. Just move this to the other side of the equation, divided by negative 100, I can get my equation 2 of the hybrid models. Okay, after I get this equation, then I substitute this I2, substitute this I1, right, into this first equations. I can now express I1 in terms of V2 and I2, right? V2 and I2 because you want to express in terms of V2, actually negative I2, right? V2 and negative I2. So after that, I get the second equation. Now the only thing to watch out is that B is actually 10, right? B is actually 10 because we're interested in negative I2 as our variable. So over here, put your B parameters as 10. So same thing, your D parameters, right, is 1. D parameters is 1, positive 1. B parameter is positive 10 because we put negative I2 as our variable of interest because of the directions of the transmission line. Now, if you want to check based on your ABCD parameters, then what you need to do is to take the determinants of your matrix. AD, right? A multiplied by D minus B multiplied by C must be equal to 1, otherwise it is not reciprocal. Any questions? Okay, the next questions basically involve modeling complex two-port networks by breaking it down into simple, right, sub-networks. And depending on whether the sub-networks are connected in series, parallel, or cascade, basically you need to use different model, right? You need to use different model. Okay, firstly is to take note that there are some assumptions for these two combinations, series, parallel. Okay, this involves a special class of two-port networks. Okay, this is a general two-port network as we know, right? You have port 1 with V1, I1, port 2 with V2, I2, and current, right, should be flow into it unless you get a transmission model, then you reverse it, right? Negative I2. Okay, but there are special classes of two-port networks like the reciprocal networks. So this is another special class we call common ground two-port network. So it's by simply shorting this terminal. That means that if this port 1, port 2 are connected together, right? Connected together, and this is usually connected to ground. So we call a common ground. Right? Common ground two-port networks. They're connected together. Then basically this is a special class we call common ground two-port network. Now, if you go to your slides again, you see this, right? This general. This is a special case where you connect these two together. And if you have two of this network with common ground connected in this form, right, that is a series combination. In this case, basically what you can do is that you can add up the impedance, okay, which means that if you model this as ZA, you model this as ZB, then you can get the overall impedance by simply add up, right, the two matrices, okay, which means that you can model this overall more complex network by modeling the sub-networks as ZA and ZB and then add them up together. So similarly, if you have parallel combinations, right? Remember for series, suppose that you have two resistors in series, right? You add up the resistance, correct? You have two resistors in parallel, you add up the conductance, right? Conductance, then you get the equivalent resistance. So same thing, if you have two-port network in parallels, right? A more general concept is called admittance. Okay, it's called admittance. So you add up the admittance Y1 plus Y2. Okay. Then you get the equivalent admittance. Okay. For this case, you get equivalent impedance. In this case, you get the equivalent admittance. This basically means that if you have two-port network in series and they have common ground configuration, then you should model them as Z parameters, right? If you have two-port networks connected in parallels, then you should model them as Y parameters. Okay, if you want other form, that means that if you have this in series, you want other form, what you do is to first write it down in Z parameters form first, then you transform it into the other form that you want, right? So same thing, if you have parallel combinations, you're asked to model it as H parameters. First, you model it as Y parameters first, add them up, then you transform this, right, into the form which you want. Okay? It can be transformed into the other three forms through algebraic manipulations or finding the inverse matrix. A cascade, notice that no assumptions on common ground, right? If you look at your notes carefully, no assumptions on common ground, because it holds whether or not it's on common ground. Okay, let's look at this last problems of our today's tutorial. We want Y parameters. Okay, and here, treat this circuit as the interconnections of two-port networks. Actually, these circuits, right, if there's no cross 2, just analyze it directly, as what we did. Right, this is basically connected together, but this question says that treat it as the interconnections of two-port network, okay, which means that you need to break it down into interconnections of two-port networks. Right? In fact, if you look at this configuration, you can see that it's quite similar to this one. Common ground, connected together, right? Connected together. So same thing over here. This is a common ground configuration connected together, right? Connected together. So over here we have a series combinations of two common grounds, right? Configurations. And here, to differentiate the input-output for these two different circuits, I'll call the upper one A, the lower one B. This basically means that my input to this subnetworks A will be V1A, my output at port 2 will be V2A, right? So same thing, V1, V2, except that I add another notation A to differentiate between A circuits and B circuits. So for B circuits, V1B, V2B. Okay, here, basically, you can see that how your V1 is related to V1A and V2A is just to add them up, right? V1 is this voltage plus this voltage. And V2 over here is this voltage plus this voltage. Right? In fact, this is Kirchhoff voltage law. And remember that I can separate this into two networks, right, which has a common ground. So this is my circuit A, this is my circuit B. I'll now proceed to model circuit A to get ZA, and then proceed to model circuit B to get ZB. And then later on, I'll try to get the overall models by adding them up, right, ZA plus ZB, because they are in series. And I can model them separately and add them up. So this is the case where if we have a very complex network, okay, if you see that there's this property of common terminals, right, at the ground terminals, then we can actually model them separately and then add them up later on, right, instead of trying to model the whole complex network, which could be more involved. So we proceed to model one at a time. This is my circuit A, right? This is my circuit A. I want to get my ZA. Okay, the rest is the same as what we have done previously. Applied circuit analysis, for example, mesh analysis. This is I1. This is I2. Then I write down two equations. In terms of the four variables, the only thing is that now we use V1A, V2A. Right? V1A is equal to voltage across the 2 ohm resistor, 2I1, plus the voltage across these 2 ohm resistors with the current as I1 plus I2, right? Inflow I1, inflow I2 equal to I1 plus I2 outflow. So you get the equation in impedance form, right? V1A is equal to 4I1 plus 2I2. Given I1, I2, find V1 of circuit A. Okay, next take Kirchhoff voltage law at these terminals. It's just V2A equal to this, which is the same as this, right? Common terminal, common branch. So share the same voltage, and it's equal to 2I1 plus I2. Therefore, I get the equation in impedance form. This is my ZA, impedance for circuit A. Okay, next, I proceed to circuit B to try to model ZB. Okay, same things, apply Kirchhoff, apply mesh analysis using Kirchhoff voltage law through loop 1 and loop 2. I can write down two equations. V1B is equal to current flowing through this resistor is I1 plus I2, right? Multiplied by 1 ohms is the voltage across it. And the voltage across here is only I1. This is only I1. So 1 I1, add them up, 2 I1 plus I2. Okay, here V2B is equal to this voltage, is the same. Common branch. I have I1 plus I2, so therefore I get ZB. Now notice that this question asks you to find the Y parameters, correct? Y parameters. But because they are connected in series, you should use Z parameters. So what we do is that we find the Z parameters, then we convert it into Y parameters. So same thing if your questions has a parallel combinations. If you want Z, right, you still model it as Y, then convert it into Z. It can also be converted into hybrid or ABCD, right, transmission. So far what we have done is that we have modeled circuits A in Z parameters form. We have modeled circuit B in Z parameters form. So we have these two modeled now. And now we shall try to combine them together, right? You can actually add these two up, but just to show you, right, why is it in series. Okay, I will show you all these steps, which is not necessary. Here you can just add them up. ZA plus ZB, you get the overall impedance. Right? Here I just show you some detailed steps on why it is in series. Okay, firstly, remember I said that V1 is V1A plus V2B, V1B. V2 is V2A plus V2B, right? That means V1 at AB circuits, V2 at AB circuits, add up, you get V1 and V2. Okay, which means that you can break it down into these two form. This vector plus this vector, right? This plus this is equal to this plus this is equal to this. Now, V1A can be expressed in terms of I1, I2. V12A, V12B, right, can be expressed both in terms of I1 and I2. So they have the same current. You can see that I replace this by my impedance model. I replace this by my impedance model over here, which I modeled. Then you can see something, right, which is very familiar. They have the same current. Okay, if the same current, you can add up this. It's just that they are matrix. So you add up elements by element. 4 plus 2, 6. 2 plus 1, 3. Right, 2 plus 1, 2 plus 1, you get 3. So this is my model, okay, in impedance form. And by the way, this is reciprocal, right? Because this is equal to this. Okay, but what you want is Y form. So what you can do is to find the inverse matrix, okay, to get the Y parameters form. Any questions? Now, if you have forgotten how to find the inverse matrix, right, but I suggest that you know that, because inverse matrix of 2 times 2 is very simple. Try to remember how to do it, right? EE2007, but if you have forgotten, it's also possible to do it in another way. It's just that you have to write down these equations. For example, V1 will be equal to 6I1 plus 3I2. V2 will be equal to 3I1 plus 3I2. Right? Then a few ways, right? These are just linear equations. Solve I1 and I2 in terms of V1 and V2. Right? Then you get the impedance, get the admittance form. Okay? So many ways to solve it. For example, eliminations. Okay, if you multiply this by 2, you get 6, correct? Then you subtract this 2. Subtract this 2, you're only left with I2 in terms of V1 and V2. You can also do that. Or you can do substitutions, right? Substitutions means that, right, let's restore the original equations. Substitutions is also fine. For example, I use the second equations to express I1, right? I1 in terms of the other two. So I divide by 3, and here I have V2, right, minus 3I2. So I express I1 in terms of V2 and I2. Then I substitute into the other equation, right? Then I'll only have V1. Then I'll only have V1, V2, and I2, right? Then you can rearrange the equation to get I2 in terms of V1 and V2. So basically it's just to solve the equations, but instead of some values, constant values over here, right, leave them as variables. That's modeling is about. Leave them as general variables and express I1 and I2 in terms of V1 and V2. Okay, so I hope everybody get the ideas. Write down the equations in terms of the 4 variables, right? 4 variables of the 2-port networks. Anything which is not in terms of the variables, relate them to the variables, like the node voltage, for example, or your dependent source, relate it to the variables, and then you get the equations, right? In terms of 4 variables, try to transform it into the desired form that you want. Okay, as for more complex networks, you have to see whether they are series or parallel, right? For series combinations, use Z parameters. For parallel combinations, use Y parameters, always, right? So that you can add up the impedance for series, add up the admittance for parallel. Okay, if the question want other form, then just transform it into other form. For Z to Y, right, use inverse matrix. Y to Z also can use inverse matrix. For other form, it's simply algebraic manipulation, which I've shown many times in this tutorial problems. Basically, you can see that when you write out the equations, right, you can always rearrange the equation into the other form. Any questions? Okay, if not, that's all for the tutorial today. Thank you.